In this video, I'm going to be talking about the circle theorem that concerns the angle between a radius and a tangent. Specifically, I'm going to be talking about the theorem that says the angle between a tangent and the radius at the point where the tangent touches the circle is a right angle. So the word tangent here means a line segment that touches the circle at exactly one point. So if this line here had gone through the circle, it touched it at 2 points, then we'd call that a chord instead. But as this one only just touches, just skims past the circle, we call that a tangent. And what this theory is saying is that if we look at the radius here and we look at the tangent, between them we have got ourselves a right angle. And because this is a theorem, this is something we can prove. Now this one's going to be a little bit wordier than the others. It's going to be a little less algebraic. We've just got to think about what's going on. So I'm actually going to start this proof off by considering what would happen if this is not a right angle. So what would happen if this is not a right angle? So what would happen if this theorem turned out to be wrong? Well, if this theorem turned out to be wrong, that this is not a right angle, then I should be able to make a right angle in a different way. By that I mean I should be able to draw a line through here, and I should be able to get a way of doing that where I have a right angle. Now you'll no doubt be looking at the screen and thinking that is definitely not a right angle, and in this case it doesn't look at all like one. So I'd be very surprised if it turned out to be one. But of course this diagram is not drawn to scale. This is not necessarily looking at all examples. This is just a generic example. So that's not actually good enough for me to say it doesn't look like a right angle. I need to do a bit more than that. I need to prove to myself that it is not a right angle. Because if that's not a right angle, then that means that this one is going to have to be. And I'll build on that in a minute. So let's suppose that this is a right angle. Let's suppose that this is a right angle. This is a 90-degree angle. Then I've just built a right angle triangle. We know that in a right angle triangle, we have our hypotenuse. And in fact, in a right angle triangle, we know that the hypotenuse, the longest length, is always the length opposite the right angle. So that's telling me that this length here, this radius here, this black length, has to be the longest length of the triangle. But of course that makes no sense. Here, these two green arrows are both representing the radius. Because it's a circle. The radius is the length from the center of the circle to the circumference of the circle. So both of these green lengths here have to be radii. And you can see that this red length is a bit longer than the radius. And it has to be. That's not just the way I've drawn it. That's mathematically it has to be because it's sitting outside of the circle. It has to be at least a little bit longer than the radius. Which means that this red length has to be longer than that black length. But we just said that if this is a 90-degree angle, that black length there would be the longest length. And so what we're saying here is that this length can't be a 90-degree angle. It can't be a 90-degree angle because that length cannot be the longest length. So if this can never be a 90-degree angle, no matter how I drew that triangle, this angle cannot be a 90-degree angle. It's impossible. Well, I've got to be able to draw a right angle triangle some way. And the only way I would be able to do that is if this angle here was 90 degrees. And so what that proves is, in a bit of a roundabout way, what we call the proof by contradiction, is that this here is the 90-degree angle.